Chapter 4 Computational Logic Design Principles. Okay, for the computational logic circuit, as you know, it's one kind of digital circuit that use only two different signals in the circuit, namely logic high and logic low, or logic 1 and logic 0. For the computational circuit, the basic property is its output depend on only the current input value. For example, if the input is 1, 1, 0, the output may be 1, 1. Okay. If I change the input to 0, 1, 1, output may be 0, 0. And if I apply the input of 1, 1, 0 again, okay, the output will be 1, 1 again. Okay. If you apply same input value, you will get the same value of the output. Okay. This is the basic property of combinational circuit. Okay, to implement this combinational circuit, normally we just use logic gate, maybe AND gate or gate. Okay, anything. You can connect it in feed-forward structure. Namely, this output will connect to the next input of logic gate, and there is no any feedback loop. So there is no something like this. This output signal cannot feedback to the previous logic gate input. So okay, and to represent the function of combinational circuit, basically we use two tables, okay, to represent or to describe the function completely. Okay. First, let's introduce some basic tools to analyze and design. Okay, that is switching algebra or Boolean algebra. Okay, switching namely open and close, on and off, or logic high and logic low. Namely, the value of each variable in the switching algebra will have only two values. Basically, we use 0 and 1. And for the terminology, okay, signal name or variable name. In mathematical term or mathematical expression, okay, we call variable. But in the circuit, for example, we may say the signal. Okay, the signal name made for at this point. For so x and y is z, right? So in equation, we may write z equal to x and y. Okay. In mathematical expression, we say that x is variable, y is variable. But in the circuit, sometimes we say x is signal, okay, signal x and signal y. So please keep in mind that it is the same, okay, it's the same. And okay, algebraic operator, maybe and we use dot, okay, or we use plus sign. Invert, okay, we use dash or prime, okay, to represent invert function. And expression, okay, expression will show the combination between variable and operator. For example, x prime invert of x and y, x or y prime, something like this. And equation, okay, have equal sign, okay, z equal to x and y prime. Axiom is the minimal set of basic definition that we assume that is to be true, okay, from all of the information about the system can be derived. For example, example 1, a1, x is 0 if x is not 1, or x is 1 if x is not 0. Okay, what does it mean? This is to define, okay, the value of the signal in the digital system. Namely, if the value of variable is not 1, it must be 0. If it's not 0, it must be 1. See? So the value can take only one of two values, 1 or 0. It cannot be 1 and 0 at the same time. Okay. And it cannot be empty. Okay. It must have 1 or 0. Okay. And example 2. Example 2 is used for define the not operator. Okay. Namely, if x is 0, x invert, okay, x prime is 1. If x is 1, x invert is 0. And for example 3, 4, 5, okay, it's for define and operation and or operation. Namely, 0 and 0 is 0, 1 and 1 is 1, 0 and 1 is 0, 1 and 0 is 0. And for all operation, 1 or 1 is 1, 0 or 0 is 0, 1 or 0 is 1, 0 or 1 is 1. Okay. Okay, this 5 examples. This is basic. Okay. Definition for the value of each variable. There can be only 0 and 1, and not operation and operation and or operation. Here, based on this 5 examples, you can derive so many theorems. Okay, for example, okay, x plus 0 is x, or x and 1 is x. Okay, this is theorem. Okay, theorem is a statement, okay, that is always true, okay, for every condition. So if you want to prove, you can prove by use the technique of perfect induction, namely just by substitute all possible value of the variable. For example, for theorem 1, when x is 0, that means this statement become 0 plus 0 is 0. It's true, right? Why? Because 0 plus 0 is 0 is axiom, right? Because of axiom, so it's true. And if I substitute x with 1, then this statement become 1 plus 0 equal to 1. Okay, this statement also true because this axiom, right? 1 plus 0 is 1. So this statement always true for every possible condition, namely when x is 0 and when x is 1. So you can prove this by perfect induction. For another theorem also you can prove. Okay. And for theorem 2, x plus 1 is 1, okay. X and 0 is 0, okay, it's okay, right? 1 or anything, okay, is 1, okay. 0 and any value is always 0, okay. This is null element theorem. Same variable altogether gets to be that variable, or and same variable and together, okay, it's to be that variable. This one is idempotency, and invert of invert, okay, is that value. is called involution. And opposite value altogether is 1. Okay, opposite value, okay, and together then become 0. Okay, this is complement. Namely, if x is 1, its complement is 0. When all together, 1 or anything is 1, right? When x is 1, inverse of x is 0, right? When and together, okay, one of them is 0, 0 and anything is 0. So you can prove something like this. Okay, well, for the next theorems, x plus y equal to y plus x, okay, or x and y equal to y plus x, okay, and all operators have commutative properties. For theorem 7, x plus y parenthesis plus z, okay, equal to y plus z first, okay. We use parenthesis, okay, to show that do this first, and then plus x, okay, the same thing. Okay, you can do this one first, or you can do y plus z first. Okay, you will get the same result. This is associative property. For and also, okay, have this property. X and y, x and z. Okay, you can write in this form x and y plus z. Okay, this is factoring or distributing. Okay, and so on. Okay, let's see the detail. Okay, to prove, okay, this theorem, okay, you can use perfect induction by substitute all possible value of variable. For example, for this theorem there are two variables, right? Then you must substitute the value of x, y with 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and if all condition can make the statement become true, so you can prove that it's always true. Okay, the theorem is true. Okay. Now let's see the detail for each theorem. The first one, okay, you can switch, right, to do x and x or y or x is the same thing. This one is easy, right? For this one, associative also the same. Well, now let's consider this expression y and z. Okay, when you implement the circuit based on this expression y and z, this one, right? Use AND gate y z, okay, add together, and then AND x. That means this output AND x, and then AND W. Okay, this output of AND gate and W. So you get the result based on this expression. How about this expression? W and x first, okay? And then and y, and then and z. And for this expression, w and x, y and z, and then these two terms and together, then we bring these two output of AND gate and together, then we get the result. So all of this, okay, you can obtain the same result. But which one is better? All of these use two input AND gate, right? 1 2 3, 1 2 3, 1 2 3, okay, same result. But for this one, every two level, that means it's faster. Okay, it's faster. Then with this one and this one, okay, can operate at the same time. So it's faster than this three level of logic gate. Okay, don't forget that each logic gate have propagation delay time. So for example, if each logic gate have 10 nanoseconds of propagation delay, that means when you apply all of this input, you must wait 1 2 3, okay, 30 nanoseconds, okay, to get the correct result. okay, but for 2 level, okay, you just wait only 20, okay, nanosecond, okay, it's faster. Okay, and well, what about this theorem? For theorem number 8, okay, if you look at the left hand side first, x and xn, okay, same, x and y, x and z, okay, xn is same part, okay, you can do factoring, namely you can move, okay, or factoring x, okay, xn, then it's become xn, right, and y plus z, okay, y plus z, okay, this is factoring. This one also you can do xr, right, the same part, then you can move this part out from y and z, then okay, actually it's the same thing, x plus y and z, okay. If there is no parentheses, yeah, you must do and first, like you do multiply, okay, multiplication first, okay, before do addition, okay, this is the same. So this is called factoring. Or if you start at the right hand side, you can do distribute, okay, you can distribute xn into the parentheses, then it becomes x and y, or x and z. This one also, for r also, okay, you can distribute x or y, okay, and then x or z, okay, x or y and x or z, okay. It's like for maybe your high school, you use something like this, p and q, right, and then r, okay, maybe okay, you can use distribute this one inside or p and or q, okay, something like this. Okay, how to prove? Okay, actually you can prove by using a perfect intersection, by substitute all possible value of x, y, and z, right? 8, okay, is possible value for 3 variable. Anyway, actually you can prove by substitute only one variable, and if that statement, okay, is true for all cases, so you can conclude that, okay, this theorem is true. For example, if I substitute x with 0, x 0, then it becomes 0 and y 0 and z 0 and y plus z. So okay, then it's 0 plus 0 is 0. Oh, it's true, right? And when x is 1, so then x is 1, x is 1, x is 1, then this statement then become y plus z equal to y plus z. Okay, then true. So that's all. Okay, because it's cover all possible case. Okay. By the way, you can prove or visualize this theorem by using Venn diagram. For example, x and y, okay, like intersect, okay, intersect. Namely, x and y, okay, this area. X and z, this area. Okay, when you all together like union, so you just combine or merge this part and this part together, then it's become this area. How about this one? X, right? This circle of x. Y or z, okay? These two circles and together, then intersect, right? So it become what? This part, right? This part, okay? That overlap together. So it's the same result. Okay. For this theorem, if you implement the circuit follow this expression, you must choose one AND gate, no, 2 AND gate, right? Namely, you must use one AND gate for x and y, and more one AND gate for x and z, and then all together you use more one OR gate. Totally you use 2 AND gate and 1 OR gate. But if you use this expression, you use only one OR gate and one AND gate, so you can save okay, that number of logic gate to implement the circuit. So based on this one, y, z altogether, and then and x, okay, then we get the result, okay, same result, but use less number of logic gate. So for the design, the first thing, okay, you must implement the circuit that give you this the correct output. But it's better if you use, okay, small number of logic gate. Okay, and for the next theorem, for this one, it's called co-free or absorption. Okay, for this theorem, it said that x or x and y equal to x. Okay, let's consider this Venn diagram. X and y, this area, all together. Okay, note this area, x and y, actually it's already one part of x. So when you all together, then it still be x. So based on this behavior, then it's called co-free or absorption. Okay, this one already cover this part, okay, this area. And for this form, x and x plus y equal to x. Okay, this is x. Okay, this is x and y. Okay, this one is bigger, and this one already inside this area, right? That means when you do intersection, so the result will be this part. Okay, if you prove by switching algebra, okay, you can do something like this. X plus x and y. So based on identity, namely x and 1 equal to x. Okay, then after that x and okay, same. So we do factoring. So x and, okay, moved outside this term, 1 plus y. So 1 plus y is 1, right? Now element 1 and x is x. Okay, identity. Okay, so we can prove by using switching algebra also. Okay, well, for this theorem, if you implement the circuit by using this theorem, based on this left hand side, you must use one AND gate and one OR gate, right? But if you reduce number of operators or and number of variable, okay, by using this theorem, okay, you can reduce it to only x. So you need not to use any logic gate, but you still get the same function. Okay, how about this one? For the theorem, x and y plus x and y prime equal to x. It is combining x and y, this part. Okay, x and y prime is this one. So note this this section and this section. Okay, when you combine it together, okay, it becomes the circle of x. Okay, so this one is then is called combining theorem. Okay, this area, okay, not overlap this area, and when combine these two parts together, then it becomes the perfect circle or value of x. Okay, to prove this one, by using switching algebra, you can using something like factoring x and, right? So x and y plus y prime, okay, by complement, okay, opposite value altogether, then the result is 1 and x is x. Okay, so very easy proof. And for this side also XOR, right? So XOR y and y prime. Okay, then you use factoring, and then for the complement y and y prime, then it becomes 0 plus x is x. Okay, so you can prove this one easily. Again, this combining theorem, okay, you can use this theorem to reduce number or size of the expression. Namely, if you implement the circuit based on this expression, you must use 1, 2, 3, 4, right? 4 logic gate, 2 AND gate, 1 OR gate, and 1 inverter. But if you use this combining theorem, okay, you can reduce to have only one variable, so you need not to use any logic gate to obtain the same result. Okay, this one also. Note this theorem, and actually another theorem also. You must observe the pattern. Namely, you not fix to x and y, but you look so in general. Namely, if for example, you can look like this rectangular and triangle plus rectangular and triangle prime. Okay, what the result? Okay. This is the same part, right? This one is opposite part. This is opposite part. I inverted here. So your result is, okay, the part that the same. Okay, and for the opposite part will be disappear. So, okay, you should understand and remember this form, okay, or this pattern. Okay, and for this one also, okay, same x, right? And opposite y prime. Okay, the result is x. Okay, how about this one? For this one, a, b, c, d, and y. A, B, C, D, and y prime. Okay, this is the same part. And this one is opposite. So the same part still be remain for the result. So they become A, B, C, and D. Okay, for the different part or opposite part will be removed. Okay, this theorem actually we use to reduce, okay, number of variable and operation. Okay, and that we will study for the next topic. Okay, and consensus theorem. For consensus, how about this one? X and y, x prime and z plus y and z equal to x and y plus x prime and z. Note this term disappear, okay, on the right hand side. Okay, this term is called consensus term. This term is consensus term. So if you use this consensus theorem, that means you can reduce this term. Okay. This term relate with these two terms by this pattern x prime. This is x and something, x prime and something. So this term and this term become this term. So this term you can remove by using consensus theorem. For this term also, x plus x prime plus y z, y z, this term can remove from the expression. This term then is called consensus term. To prove this one, for example, let's try to prove this one by using induction. X, let's consider this one, y and z. When y and z is 0, this term becomes 0. So now left hand side and right hand side become the same, so it's true. And if I give the condition y and z is 1, that means y must be 1 and z also must be 1. So I substitute y with 1, z with 1. YZ is 1, 1. So after you substitute value of of y and z with 1, you get the same, right? Same expression for the or the same value, right? For this side, 1 plus anything is 1. And for this side, x plus x prime is 1. So it's true. So you can conclude that this statement is true. Or you can use switching algebra to prove. For example, let's consider this one, y and z. I add add 1 to and with this term, and I consider 1 as x plus x prime. Same value, right? And then I distribute this term, so it becomes x and y and z, x prime and y and z, and then this term I add 1 at here, x and y and 1, and this term, x and y, the same part, right? So I factoring from 1 plus z. This one also x prime z, x prime z. So by factoring x prime and 1 plus y, 1 plus any variable become 1. 1 plus y is 1. 1 and x and y is x and y. 1 and x prime and z is y, x prime and z. So QED. You can prove by using switching algebra. To prove each step you must be sure that you use some theorem, use some theorem or axiom to process each step. So each step must keep the same result or the same value. And another theorem for n variable theorem. For example, x plus a is x, x and a is x. It is generalized idempotency or invert of x and x1 and x2 and so on. So you can distribute invert to each variable and change n sign to all. Change n to all. or invert of this variable, then you can change all to n. And if you mix between or and operators, okay, you can distribute this inverter, okay, to each variable, and then switch all to n, okay, the position that have n change to all. So this De Morgan theorem. Okay, furthermore, for Canon theorem, Shannon's expansion theorem, for any function with x1, x2, and so on to xn, you can write the expression of the function by x prime, okay, about some variable. For example, you can do the expansion about x1. So you can write this like this expression x1 and the function that x1 is 1, and this term is x1 prime, and the function that x1 is 0, okay, and then you are okay add these two terms, okay, together. So to prove this one is very easy, right? We just consider, for example, when x1 is 1, when it's 1, so this term becomes 0. So it's 1 and the function that x1 is 1. So it's the same, right? Yes. And when x1 is 0, then 0 prime, then it becomes 1. So this term is 0, right? This term is 1 and the function that x1 is 0. So it's the same. Okay. Okay. Now to prove. For example, I want to prove this one. How to prove this? Okay, based on the theorem, x plus x is x. Okay, this one is correct, right? Based on the theorem number 3. Okay, x plus x is x. But there are only two variable of x, right? So for 3, 4, 5, okay, till now that there is no any theorem to support, so you must prove. To prove this one, you may use finite induction. Namely, this for n variable, when number of variable is finite, okay, not infinite, okay, you can prove by using two steps: basis step and then induction step. Okay, the idea is something like this. The basic step, you prove for the small number of variable. For example, only 1 or 2, okay, variable. Okay, and then you for the induction step. For induction step, you assume that if there are, for example, I variable, you assume that in the case that I variable is 2, and then you must prove that if there are I plus 1 variable, you must prove that is true. Okay, namely, assume this case is true, and then if this case is true, if you can prove that the next I plus 1 is true also. So that mean in general you can prove that this one is true, right? So for the basic step, you can show that at the beginning, or the smallest number of variable is true. So based on induction step, that means if this term is true, the next one also true. Then when this one is true, so the next one, okay, then become true also. When this case is true, so the next one then become true also. Okay, so this statement, okay, you can prove by using this math inductions. Okay. Okay. For example, if I will show you how to prove this theorem. To prove this one, basic step indicates when n is 2, okay, x plus x is a. Okay, based on theorem number 3, and then I assume that in the case that there are I term, okay, I term, namely x plus x plus x I term. Assume that is x, okay, x plus x plus x equals x is true. So I must prove that, I must show that x plus x plus x plus x I plus 1 term equal to x also. So how to prove this one? It's very easy, right? Okay. This one is I plus 1 term, right? So that means it's x plus x plus x plus x I term. And based on this assumption that when n is I, number of variable is I term, so it's equal to x. So that means you can write, okay, x, okay, for this term. Then it becomes x plus x, and x plus x is x also. So based on basic step and this induction step, okay, you can prove. Okay, and for De Morgan theorem, is some kind of like this. Okay, for example, maybe in your junior high school, maybe in high school, maybe using this symbol invert p and q. Okay, for example, equal to invert p or invert q, right? Something like this. Or invert p or q equal to invert p and invert q. So you can distribute, okay, invert inside to the each variable, and then change n to all and change all to n. Okay, this one also the same. Okay, distribute invert, okay, to each variable, and then change n to all or change all to n. So how about this one? X and y and then invert. This function is nan, right? Nan function. So actually for this one, if you use De Morgan theorem, you can show that x and y, okay, prime equal to x prime or y prime. So to implement the circuit, you can use what? OR gate, right? Invert x first and then invert y. So the result of inverter x prime and y prime, okay, all together, okay, you get the same result of NAND function. Okay, same thing. Okay. By the way, okay, for AND gate, do this one, right, and then invert. You can keep just with this inversion bubble. Okay. So this is and the symbol of NAND gate. How about this one? You can do the same thing, namely this OR, and you keep this inversion bubble, okay, and move, okay, to here at the input. So this one also NAND gate, okay, different symbol but same function. So please remember. This is the new one. Okay. For this one also, invert of or no. Okay, you can use thermogan to show the expression like this: x plus y prime equal to x prime and y prime, right? So to implement this one, okay, you use this x prime, y prime, use inverter, right? And then and together. Again, you can draw the logic symbol by using this and then this invert at the input. Okay, this one also no. Okay, no get, no function. Okay, different symbol but the same function, so it's equivalent together. So please remember. How to remember? Okay, how to remember? Actually, you can do something like this. Let's imagine if I move this inversion bubble from output side to the input side. Let's move. Okay, move, and then we pass through this body, right? Then this gate body will change. If at the beginning it's AND structure, so it will change to OR structure. Okay, the body will change from AND to OR, and then this inversion bubble, okay, will move to the input side, so that it become this logic symbol. Or if you have this one, you can move this inversion bubble, this circle, from input to the output side. Again, when you pass through this body, okay, the body will change form, okay, from R to N, then from R to N, and inversion bubble can move to the output. Okay, something like this. Okay. For this one also, if I move this bubble from input side to output side, and this body will change. If at the beginning is AND body, so it change to OR. Okay, that's all. Okay, let's try to imagine in your brain or in your head. Okay, the next page is show the generalized theorem again. Okay. Namely, for invert of function f, then you can distribute this invert to every variable of the function, and the position that are get changed to n, and every n operators change to all. So the generalized De Morgan theorem. That's swap between and all. Okay. So if I want to find out the invert of this function, invert of this one, okay, the result should be A, B, or C. Which one? Okay, based on this one, if you do by consider this one, invert, right, for every variable. So W prime, then it becomes W, change N to R, change X to X prime, change R to N, change X to X prime, change N to R, change Y to Y prime, change R to N, change W to W prime, and so on. Okay. For iteration A, this one is correct or not? No, not correct. Why? That because at the original expression, we do this W prime and X first, right? x and y first, right? W and x and y, W and x and z prime first, right? And then all these terms together. But for this expression, you write this one. What happened? You must do and first, right? But this one do W and X. So what's wrong? Yes, you forget parentheses. Okay, you should add parentheses. Okay, to keep the order of operators. So don't forget. Okay. Okay, for this question, the answer is C. Okay, don't forget the precedence of operation. Okay, should be maintained okay, for the original one and the second one. Okay, that's all for today.